Okay, so hello everyone. This is going to be a little bit more general presentation. So I will go through our haptic platform that we have developed for a long time now, and with some partners here. I will come back to that a little later. So this simulation is about education and training on surgical and medical applications. Just before going through the application, I just want to show a little bit where we're from. So we're from CEA. CEA is a big research center with more than 16,000 people in France, and there's a technical department there. And the technical departments do many things from electronics to energy and, of course, haptics on what we are. So there is three main institutes. We have LETI, we do electronic, LITEN, we do more about energy. And we are from the LIST. The LIST is actually the institute who integrates everything. So everything that has both electronics or robotics coupled with software will fit in our lab. And so we have we work on user experience, system integration, simulation, and so on that. So there's many of this. And personally, so in this institute, I'm from the Sensorial and Ambient Interface Laboratory. So we're situated in Paris, and we're specialized in tactile rendering, touch sensing, and mechatronics, basically. And we develop technology about that. So a lot of surface tactilization, new active and semi-active technology. So I will come back to this one. This is the important one. So magnetorheological fluids, also IoT and so on. And we have application on many aspects here. So the topic of my talk would be to present the skills platform that is now twofold. We have one platform which is on the left. It would be the first part, the surgical training. So I will go fast on this one because there's no SOFA running on this side for the moment. And after that, I will talk about our approach of medical education, and specifically on the goal to have some very inexpensive and reliable systems using smart materials. And our application are what we call dynamic anatomy. So this is bringing early on the courses to the curriculum to bring how to teach force and how to sense force while learning anatomy. Okay, so for the first platform, this is the skills platform. It started a long time ago. In 2006, it was a European project. And so the goal here was to make a platform that was very accurate from a haptic point of view and for open surgery, or for both endoscopic and minimally invasive surgery and open surgery. And for this matter, we developed some specific robots that you see here that are able to actually simulate accurately the interaction of the surgical tools on the virtual patients. And so this is an hybrid technology, and it can go up to 6,000 Newton per meter. So it is also possible to simulate bone surgery and especially drilling, and this is what we have done. There is two platforms right now. The first one that was developed during the European project here that are in CEA, and this one that was sold to the hospital of Amiens. And it was a technological transfer to the two companies, Epsion and HRV, which is also a French company on that. Here is the robots. I will not detail that because I don't have the time for this. This was a video, but you see how we do the operation on the robot here. So right now we're getting rid of the screen to put VR goggles, and that's what we have today. So what's interesting with that is that the platform was actually evaluated, and it was evaluated as an assessment tool. So we used 3 different groups of different expertise and make them do a bone surgery, a bone drilling surgery on the platform, and put a graph of their performance as precision versus efficiency. And what we saw is that the three different groups are well separated, with the novice that are here, that are very fast but extremely imprecise, the intermediates that know the surgery, that are quite precise but quite slow, and only the experts that are here, that are both precise and efficient. So it was a nice result, because this kind of platforms, it's difficult to evaluate and assess this kind of platform, but here we can have that. And furthermore, you see with the red arrows we have here that we actually have the signature of a learning curve here, which is this form of getting the precision, and then the efficiency is usually what you get on motor control training. Okay. So now we have our two platforms, but we had some economical consideration. Right now, I must admit that these platforms are research platforms due to their cost. So we try to find a way to actually extend our application. To do so, we have to lower the cost. And we lower the cost by reducing the number of moving parts in the system, and by using smart materials. So I'll try not to go too fast after that. The other aspect, the other approach is that we can notice that in haptics, resistive force is usually largely predominant. There is very little strong driving force in virtual reality. And so we can use brakes instead of motors. By doing so, the control loop is much easier to get more secure and so on, and it's much more easy. We don't have to go up to a frame rate of 1 kHz to have the haptic feedback correct, and this is a good thing. So we have a technology that is based on magnetorheological threads. So I will not go in details with that. This is simply an oil with polarizable particles in it, and when you apply the magnetic field, they align, and it gives you the possibility to tune very precisely the viscosity of the fluid. So if you have a disc running into this fluid plus a magnetic field, then you have a very nice control of your braking force. It is very fast. The response of the system is more instantaneous, and you have a very good energy density, the size compared to the torque you can get. And this is an example of our on our device here. So we find some few applications to apply this technology. I will talk only on the first one here. This is the cruciate ligament diagnosis. Why this one? Because it was orthopedy, so a huge market on this one, but also because this was 1 degree of freedom, and it was easy, and so it was a good way to start the development. Then right now we're developing a mandibular luxation treatment platform, which has 3 degrees of freedom, and that's it. I will detail the first one on this one. Here it is. So this is this movement is called the Lachman test. So on this one, we're working with the company Anatoscope, which is using SOFA. And so all the simulation here is in SOFA, coupled with Unity, and is interacting with our device, which is here. You can see here the very first prototype, which is just a leg, basically. And you can see here the hardware is very simple. You just have a brakes, a belt, and a pulley, and that's it. We don't have anything else, no reduction, no complex mechanics or anything, and it helps a lot to reduce the cost. The SOFA simulation is that simulate the ligament is made with a chain of strings, and you have the ligament that are following this chain of string. Also, the simulation is mapped, so the simulation is largely pre-calculated to improve the speed of the calculation in this application. So the platform was tested. So on the top, you see it was evaluated in Amiens with surgeons that have tried the system. We have also tested the system with an arthrometer. So an arthrometer is a system that is used with patients to measure the laxity of the knee, and we can also put our robots on it and see the different systems. So on this one, it was a little bit too soft still, because on surgery, on this kind of application, we always discover that what the surgeons thought they were doing is not what they were doing. So they were applying way more force way faster than they were thinking on the things. And so we have made a second version, which is actually my last slide. Here it is. So this is the version of the dynamic anatomy system, where you see the leg here with a better integration within a silicone skin. On the back, you see the surface simulation that can give you all the anatomy you want. You can choose the muscles, the bones, or whatever, and it moves. If you move the legs, it moves on the simulation, and you have all the information. And so all of this was there was publication last year on that. And just a word on the three main partners. Sorry. So of course, Anatoscope. I've already talked about that. The work has been done on the institute, on the Facing Faces Institute, which is an institute in Amiens. And all of that was done also with SimuSanté. SimuSanté is a big platform for training and simulation in Amiens. And they were part of the project. So I think I'm done. Oh, yes.
Perfect.
Voilà. Thank you very much.
Yeah, thank you very much, Sylvain. Is there any question further to the presentation first? Otherwise, I would have some as well. As we did before, for those who just joined this afternoon, you know, there is always a time for questions. So 5 minutes after the presentation, you can either post your question directly in the chat or unmute yourself and ask the question directly. So do not hesitate to raise a hand or post a question. I see. I was just checking for a raised hand, but. Yeah, for I had a question about the model of ligament that you are actually using. Do you know a bit more about it? You know, you said it's a set of strings, but it's, you know, a line model, and there is strings on there on this line, and that's the stiffness, I guess, of this string that you can adapt, or is there a 3D model and how it is attached?
And so yes, the string I attached to the bones that are considered as rigid body, basically. But on the detail of the algorithm used, I can't tell you, because this is technology from the company, and we don't have access to this, basically. So if you want more information on that, this is Elie Caton that have done this work in Anatoscope, and I'll be very happy to get you in touch so that I can tell you more.
All right. I understand the focus is really on the haptics. It's actually quite interesting. We're going to have also later on a company from Sweden that will present a set of you know, an approach for building a new generation of you know, affordable haptic devices, which is Follow. Mm-hmm. So I think there could be nice connections here as well. There was also earlier this morning the presentation of Insimo, where they are also connected, you know, to medical centers, a bit like at Amiens, where you went. So yeah, if there is any question from the audience, we could take another one. Are people either getting shy? Frederick, perfect.
Yeah. These motors, these actuators that you use, the magnetic rheological fluid, will they provide only a braking or a viscous damping actuation, or will they provide also an active actuation?
They can also, yes, we have a version of the brakes that is hybrid brakes that you have both brakes and electric motor connected, and we have the controller to control both at the same time. And so basically this is for applications with in a situation where you are much more resistive force, and then you need little driving force, active force in the system. And so we have demonstrators in that also, so we can do both on this aspect.
Okay, so this actuator that you use, is it a combination? Is it a hybrid of these two? Or
on this application, no. In this application, we use only resistive force, because the doctor does not use at all the feedback. Not the feedback, the return, the elastic part when the knee goes back to its position. So the only thing we have is that we have a spring inside the mechanics that is putting back the knee on its normal position. That's it. But we can put some, for other application, we can put some hybrid system, yes.
Okay, interesting. Have you developed these actuators yourself, or?
Yes.
Or, yeah,
yes,
okay.
Well, there's several people doing this kind of stuff, and we have a design that is patented by CEA, and we develop everything in the lab right now, so we can dimension the brakes as you wish on that. The only limitation is that the bigger the brake, the more friction you have without magnetic field. So it's a trade-off between minimal and maximum torque you can get.
Okay,
thank you very much. Very impressive. I have more questions. We can take them later.
Yeah,
yes.
Exactly.
No
Thank you, Frederic. Sylvain, so that you know, we have we're going to have the session with again two other presentations, one from Infinitec 3D and one from Folu, with Frederic that just asked you a question, and then we're going to have a break time during which there will be actually people that will be able to ask you further questions further to your presentations. So there will be dedicated rooms for that. So thank you again for your presentation, Sylvain.
Thank you.